Welcome in, everyone. In this video, we're going to talk about transformations of parent functions, identifying what those transformations are, and then as well as get into a couple examples of graphing transformations of parent functions. So the two basic ones we're going to talk about today are quadratics and absolute values. So our quadratic parent function is just y equals x squared. And then we have a couple of different things, either by lead coefficient or horizontal vertical translations, a, h, and k, we can do to manipulate this parent function to make a new function and graph that. As well as the other one we're going to look at is absolute value, where again, notice the a, h, and k essentially show up in the same spot, where h is inside the operation that defines the parent function, and the k is on the outside as well as a is on the outside. And what you're going to notice is what's inside is going to affect the horizontal aspect, and what's outside is going to affect the vertical aspect. Okay, so let's first look at what a is going to do to our graph. First off, if a is negative, that means we are going to have a vertical reflection. Okay, vertical reflection, and you can also include over the x-axis, which means all of our positives become negatives as far as y goes, and all of our negatives become positives for our y values. The next thing is if the absolute value of a is greater than 1, then we are going to have a vertical stretch by factor of the absolute value of a. If the absolute value of a is less than 1, and I'm going to kind of clarify greater than 0, so it's usually going to be a fraction between 0 and 1, then we are going to have a vertical compression by factor whatever the absolute value of a is. Okay, so a really affects whether we flip this graph over the x-axis and how far we stretch or compress it down, or by how much we stretch or compress it. Okay, the next part is our h, and notice in here we have a minus h. Okay, so there's a couple different ways to look at it. I'm just going to kind of lay it out straight where we want to think of the opposite sign. So a lot of times I tell people to change the sign when we think about what h is going to do. But both of them are going to be translations. So if we have a minus h, because that h is positive, we're subtracting a positive number, then we are going to have a horizontal translation right. Okay, if we are subtracting a positive. Now, if h was negative, meaning we're subtracting a negative, when we subtract a negative, it turns into a plus. So if it looks like we're adding h, we're going to have a horizontal translation left. Okay, I like that the h is our horizontal translation. Kind of helps clue us in that h is the horizontal and k is the vertical. The last part, k. Okay, this one we're going to keep the sign, k for keep the sign. If we have a plus k, that means we're going to have a vertical translation up. If we have a minus k, we're going to have a vertical translation down. All right, so those are going to be all the factors. We've got 7 different transformations that we can undergo. Usually we're only going to have 2 or 3, maybe up to 4, but we pick it out from those. So I always like to read these left to right, take into account my reflection or stretch or compression vertically first, and then worry about my translations, because the translations are just counting right, left, up, down from there. Okay, so our first example. And when we do all this, we want to first identify what type of parent function it is. So because we have this square here, we know that this is a quadratic parent function. And our quadratic parent function looks like this, where we have our vertex at 0, 0, and then we have a point at 1, 1, negative 1, 1, because whatever our x value is, when we think about that parent function, y equals x squared. If x is 1, 1 squared, 1 squared is going to be 1. If we have 2 for x, well, 2 squared is going to be 4. 4 right here. And then even if we can go as far as 3 and negative 3, 3 squared would be 9, 5, 6, 7, 8, 9, and here. So I'm going to sketch this the best I can. So that's our parent function, and that's what we're going to transform. That's what we're going to either flip or stretch or compress or move up, down, right, left. And we're going to determine that from what our different transformations are. So as we go left to right, like we would read, we have a negative here. Well, that negative automatically means a vertical reflection. And you can say over the x-axis. And then we have 2. 2 tells us we're going to have a vertical stretch. By factor 2. Then we have a minus 3, so that's going to be a horizontal translation, right 3. And then the plus 1 tells us a vertical translation up 1. Okay, so those are all of our transformations based off that parent function. So what I always like to start with is our vertex of our parent function, because if we're at 0, 0, this point is not going to be affected by any reflections or stretches or compressions. Because if we take this point and we reflect it over the x-axis, it's going to stay at 0, 0. When we vertically stretch or compress, really we are going to multiply that y value by whatever we're stretching or compressing it by. And because my y value here is 0, well, 0 times 2 is still going to be 0. So really this vertex, this point at 0, 0, is only affected by our translations right, left, up, or down. So that vertex at 0, 0, I'm going to go right 3, 1, 2, 3, and up 1 right here. So my new vertex shifted right 3, up 1. Next, we're going to look at our point at 1, 1. And if I reflect that over the x-axis, I'm going to be here at 1, negative 1. And then I'm going to stretch it by factor 2. Well, the distance it has from the x-axis is 1, and 1 times 2 is going to be 2. So what that point 1, 1 becomes 1, negative 2. Notice that y value, we really just ended up multiplying by negative 2 right there. So that's something you can use to kind of help you out. Hey, the vertical aspects are what affect our y. So I'm going to take negative 2, or that 1, 1, that 1 becomes 1, negative 2. And then I'm going to go right 3, 1, 2, 3, up 1, right there. Okay, and I can do the same thing for 1, negative 1, or sorry, negative 1, negative 1. Negative 1, negative 1 is going to become negative 1, negative 2. And then I go right 3, 1, 2, 3, up 1, right there. Next, I have 2, 4. Well, 2, 4 is going to become 2, negative 8. 1, 2, 3, 4, 5, 6, 7, 8 after I reflect it and stretch it. And then I go right 3, 1, 2, 3, up 1, right there. And one thing you can also help yourself out is your axis of symmetry goes right here. Okay, so if my axis of symmetry is going through my vertex right here, well, it's going to be, the point associated with it's going to be on the same level or on the same y, just with a different x, with the same distance from our axis of symmetry. So I have 1, 2, go back to my axis of symmetry, I go 1, 2, right there. Now you can still take that -2, -4 to make it -2, -8, and go right 3, up 1. That works just the same. But you learn to find, after you do a couple of these, you learn to find shortcuts and patterns you see with all of them. And so there's going to be our new graph. Notice it should now be pointing down, it should now be steeper, and move to the right 3, up 1. Our next example is going to be an absolute value. So I have y is equal to 1/2 times the absolute value of x plus 4. So I have a absolute value. I'm going to go ahead and our absolute value is y is equal to the absolute value of x. And that parent function would look like this, where again, when x is 0, y is going to be 0. When x is 1, y is 1. When x is 2, y is 2. When x is -1, y is 1. When x is -2, y is 2. And it would do something like this for our parent function. Now, you don't have to graph your parent function every single time you do transformations. I'm just doing it now so that we can see how these points get transformed by what we have going on in our equation. Okay. Now, I don't have a negative, so I'm not going to have a vertical reflection. I do have a 1/2 here, so that's going to be telling me a vertical compression by factor 1/2. I've got +4, so that's going to be a horizontal translation. And because it's +4, it's going to be left 4. And then -5 tells us a vertical translation down 5. So again, when I start here, I'm always going to start with my vertex. Okay, it's not going to be affected by the compression, because if it's sitting on this x-axis and I compress it by a factor of 1/2, it's still going to be sitting on that x-axis. From there, I'm going to go left 4, 1, 2, 3, 4, and down 5, 1, 2, 3, 4, 5. Okay, and then I look at my point at 1, 1. Well, 1, 1, if I compress it by half, so the distance from the x-axis is 1, well, half of that distance is going to be 1/2. And then from there, I'm going to go left 4, 1, 2, 3, 4, and then down 5, 1, 2, 3, 4, 5 right here. For that -1, 1, well, I compress it by 1/2, becomes -1, 1/2, and then I go left 4, 1, 2, 3, 4, down 5, 1, 2, 3, 4, 5, right there. Next, I look at 2, 2. Well, if I got 2, 2, the distance from the or the x-axis is 2. I compress that by a factor of 1/2, it becomes 2, 1. And then I count left 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. Next, I have -2, 2. Compress that by a factor of 1/2 along the y-axis vertically. It's going to become -2, 1. 1, 2, 3, 4, 1, 2, 3, 4, 5, right there. Okay. Now you may notice some of the points did not land on nice whole coordinates. Okay, so what you can do as we get farther and more in depth into this, maybe we have different values like 1/3 or 2/5. What's going to make it easier for you is find your outputs that are divisible by whatever is in the denominator. So one thing you may notice is I have a point here at 4, 4 along this. Well, I may pick that point and skip 3, 3, because 3, 3 is going to end up being 3, 1.5, and I want to try and avoid decimals or fractions if possible. So I can think of that one at 4, 4 becomes 4, 2. And then I move that left 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. Right there. And so I'd have this right here. And then right here we have this. And that would be our transform. And notice, what started out as a slope that looks like 1, 1, because it's a slope that looks like 1 over 2, what our A value was. Kind of works like our slope for our absolute value. Okay, so that's going to be it for this example. I'll see you all in the next one.